Hi, this lesson is about the definition of a limit. So here's the notation. This is read as the limit as of f of x as x approaches a equals L. This means that the closer x gets to a on both the left and the right side of a, the closer f of x gets to some value that we're calling L. L must be a finite number. So basically, a limit value is a y value or a graph that's getting close to a y value. So there's going to be two different scenarios where a limit will exist, and those scenarios are here. So in the first example, I have the graph of a function where you can see that here's your value a, and so imagine getting closer and closer to a on the left side and on the right side. So on the left side would mean numbers less than a, and on the right side of a, meaning numbers greater than a. And then if you look at what the path of the function is doing, well, when I'm on the left side of a, it's getting closer to this blue point, and when I'm on the right side of a, the path of the function is getting closer to the same blue point. That blue point is f of a, or the value that we call L. So the limit value is equal to f of a called L. And so in this case, when it is converging to a point that actually exists on the graph, you can say that a is in the domain, and therefore the limit value and f of a are the same. Okay, so in the next example here on the right, you still have this value a. So imagine getting closer and closer in a on the left side, and then following the path. And so the path of the function is getting closer to that open circle. And when I get closer and closer to a on the right and I follow the path, well, that's also getting closer and closer to that open circle. That open circle corresponds to the value of L, or f of a, but in this case, f of a does not exist, meaning a is not in the domain. So the limit exists, but f of a does not. And that's okay. You can have a limit value that exists, but a function value that does not. Okay, one-sided limits. When considering the limit of a function from only one side, left side or right side, we call those one-sided limits. So the notation looks like this. This is the limit of f of x as x approaches a from the left. The minus sign to the right of the number a, because a will be a number, represents from the left. And here, the limit of f of x as x approaches a from the right, well, that's indicated by a little plus sign next to the number. A could be any real number, but the positioning of this negative and this positive means either from the left or from the right of a. So, by definition, the limit of a function at a exists when the left-hand limit and the right-hand limit are the same. So this definition here in the box is something you should memorize. The limit as x approaches a of f of x equals L if and only if the limit as x approaches a from the left of f of x equals L, and the limit as x approaches a from the right of f of x equals L. So now that we know the definition, let's look at some examples of where the limit does not exist. So let's start with example 1 here on the left. So suppose you're considering the limit at 2. So as you get closer and closer to 2 on the left and you follow the function value, your function value is approaching this point here, which has a value of 3. So the left-hand limit is equal to 3. But when you're on the right side of 2, the path of the function is this line that's here on the right, and that function value is converging to that open circle that has a function value of 0. So the function does not exist there, but notice that the path of the function as you get closer to 2 on the right is getting closer to that open circle. So the right-hand limit is equal to 0. Since the left-hand limit and the right-hand limit are not equal, you can safely say that the limit does not exist, as indicated here, DNE, meaning does not exist. But in this example, the function does exist, but it exists at 3. That's why you have the closed circle here and an open circle below. You can't have two closed circles corresponding to the same value of x, because then that would violate the definition of a function. All right, so let's look at the example here on the right in purple. So I have the limit as x approaches 1 from the left of f of x. As you get closer and closer to 1 on the left side, the function value is approaching 2. As you get closer and closer to 1 on the right side, the function value is here below, approaching negative 2. Once again, your right and left-hand limits are different, and therefore the limit of the function at 1 does not exist. And also, f of 1 does not exist. That's why you have open circles both here and here that correspond to the value of f of x at 1. It's undefined at 1, but the limit from the left and the right do exist. The limit overall does not, because the left and right hand limits have different values. Okay, here's another example of a limit that does not exist. Remember, by definition, the limit exists if the left-hand limit and the right-hand limit converge to the same finite number, and we were calling that number L in the definition. Well, here, if we consider the limit as x approaches 0, if I'm on the left side of 0 and I follow the path of the function, well, the path of the function is going in that direction, so that is approaching negative infinity. That's certainly not a finite number. Now let's look at the limit from the right side. As I'm getting closer to 0 on the right and I follow the path of the function, that's going towards positive infinity. So both the left and the right hand limit, not only are they different, but they're not finite numbers. Therefore, limit does not exist at 0, and also f of 0 is undefined. Actually, your y-axis looks like it's an asymptote to this function. All right, so let's look at limits from a numerical perspective. So suppose I wanted to compute the limit of this function. So you know for sure that it does not exist at 1, because if you plugged in 1, you would have division by 0, and that's undefined. But it is possible to have a limit value that exists, although the function does not, as we've seen in previous examples. So we're going to compute this numerically. What that means is you're going to pick values that are close to 1 from the left side and the right side of 1. So here are my x values. Notice that this is the left side of 1. So 0.9 is close to 1, 0.99 is even closer. And when I plug them into y, and y is your function, the y value is x squared minus 1 over x minus 1. When you plug that in, I get the values here below. When you plug in 0.9, your y value is 1.9. When you plug in 0.99, your y value is 1.99. Now we have to do the same thing. So this was the left side. Now we do the same thing from the right side of 1. So I pick values close to 1 that are greater than 1. So 1.1 is close to 1. 1.01 is even closer. When you plug into y, again, y being the original function that you're taking the limit of. So when you plug in 1.1, your y value is 2.1. When you plug in 1.01, your y value is 2.01. So what that means is the closer you get to 1 from the left side and the right side, it looks like my y value is getting closer and closer to 2. So that's what you conclude to be your limit value. Now, if I take this same example and I graph it, you can actually see it in a graph. So a little trick for graphing a rational function like this. If I took that rational function and I were to factor it, the numerator factors as the difference of perfect squares into x plus 1 and x minus 1. So when I factor it, the x minus 1 in the numerator and the denominator cancel, meaning that this function reduces down to this, x plus 1, which is a linear equation. What that means is when you graph it, it's going to look like a line, but remember, it doesn't exist at 1, where your limit value is approaching, because at 1, it's undefined. So when I graph this, so your y-intercept here is 0, 1. This is 0, 1. And remember, as x gets closer and closer to 1 from the left and from the right, my y value is 2, which is this point right here. So when you connect those points without filling in the that open circle, because it's undefined there, you can see that as you get closer and closer to 1 from the left and the right, your function value is getting closer and closer to the value of 2. Okay, so here's a couple of left and right hand limits of functions that hopefully you remember the graphs of, because you really do need to know the graphs in order to evaluate these limits. So the first example is asking you to evaluate the limit as x approaches 0 from the right of ln of x. The graph of ln of x looks like this. So I'm only interested in the right-hand limit because the domain of the natural log is all positive real numbers. So natural log doesn't exist to the left of 0. So as I get closer and closer to 0 from the right, if I look at the path of the function, that is approaching negative infinity. That's your limit value. That limit does not exist. Again, because it's not a finite number, and it doesn't exist as a finite number from the left or right, from both the left and right side of 0. Okay, let's look here on the right. I have the graph of tangent. Remember, tangent has infinitely many vertical asymptotes at pi over 2 and every pi units to the left and the right of pi over 2. So here's a couple of periods of the graph that I've drawn, and I'm interested in evaluating the limit on the left side of pi over 2. All right, so here's the left side of pi over 2. If I look at the path of the function, well, this is approaching positive infinity. So again, this is another limit that does not exist because it doesn't converge to a finite number, and the behavior is also different on the left and the right side of pi over 2. Okay, so here different information is being provided. We want to sketch the graph of f of x that satisfies the following conditions. These are the conditions, and we have to come up with a graph that satisfies these conditions. We want to show a graph where the limit as x approaches 0 from the left of f of x approaches 1. We want to show that the limit from the right of 0 approaches negative 2, and f of 0 equals 1. So this is the only actual point that you know on the graph. You know that at 0, y is 1. So that's the point that I plotted right here. Right? Then I have to deal with the limits. So from the left side, it has to be getting closer to the value of 1 along the y-axis. So that means you need to show some sort of graph to the left of 0, and it could look like a curve the way I did. You could also draw a horizontal line. The curve could go downward. The shape to the left of 0 doesn't really matter. What it matters is what happens as you get closer and closer to 0 from the left. The function value has to be getting closer and closer to 1. So this graph works. Now from the right side of 0, so now I'm here, I have to show that my graph is approaching negative 2. But remember, I can't color in 0, negative 2. If you have two solid points along the same vertical line, it's not a function. So this will be an open circle at negative 2, and then you want to draw some sort of graph to the right of that value. And again, it could curve up, it could curve down, it could be a horizontal line, as long as you get your graph shows that as you get closer to 0 on the right, your function value is getting closer to negative 2. Okay, so here's another one of those examples here in blue. We want to sketch the graph of f of x that satisfies the following conditions. So the first condition is that the limit as x approaches negative infinity approaches 0. The next condition is that the limit as x approaches 0 from the left approaches infinity. The next condition is that the limit as x approaches 0 from the right approaches negative infinity, and the limit as x approaches infinity approaches 0. So if you look here on the right, the graph is actually a very simple graph. So let's make sure that all of this works in terms of my conditions. So the limit as x approaches negative infinity approaches 0, well, that's the behavior that you see right here. The further your x values go to the left, your y values are getting closer and closer to the value of 0. Now the next condition, as x approaches 0 from the left, the function goes to infinity. Well, that's this part right here. As you get closer and closer to 0 on the left side of the y-axis, the function value gets very, very large. Okay, so we took care of the first two conditions. Now let's look at the next two. As x approaches 0 from the right, your function value goes to negative infinity. Well, that's the behavior that you see right here. So as you get closer and closer to 0 on the right, your function value goes to negative infinity. And as x goes to infinity, your function value goes to 0. Well, that's the behavior that you see right here. As your x values get very, very large, your y values get closer and closer to 0. Okay, so these sketching problems take some practice, so make sure you understand the concept and how to read limits before you try to sketch based on conditions. Okay, if the value a is in the domain of f of x, then the limit as x approaches a of f of x can be evaluated by a method called direct substitution. So when a is in the domain, this is actually the easiest way to compute the limit. So here are some examples. I want to evaluate the limit as x approaches negative 1 of x squared minus 2x plus 3. X squared minus 2x plus 3 is a polynomial. It's a quadratic function. All real numbers are in the domain. There is no restriction. So as I get closer and closer to negative 1, it's actually the function, or the limit value will be the function value. So by direct substitution, that just means you plug in negative 1 into x squared minus 2x plus 3. And when you do the math on that, you get that the limit value is 6. Now let's look at part B. I want to evaluate the limit as u approaches 2 of 2u plus 5. Now, radicals do have restrictions on the domain, but as long as the value of u does not result in a negative inside of the radical, then you have a real number result, and therefore it's in the domain. So 2 works. If I were to plug in 2 in for u, you would get the square root of 2 times 2 plus 5, which is the square root of 9, and that has a limit value of 3. Notice that when I plug in the number, I no longer write the limit. So here, once I plugged in negative 1, you don't write the limit in front of the expression. You're just evaluating the function at that value. Okay, so now let's look at part C that's here. We want to evaluate the limit as theta approaches pi over 4 of sine of 2 theta. So sine and cosine have a domain of all real numbers, so theta could be any number. So when I plug in theta, you have the sine of 2 times pi over 4. The 2 and the 4 cancel to just 2 in the denominator. So you're evaluating the sine of pi over 2. That's an angle you should know. It's a quadrantal angle, and the sine of pi over 2 has a value of 1. Therefore, the limit has a value of 1. Okay, now I'm here on the right. I want to evaluate the limit as x approaches pi over 3 of 2 tangent of x. So we just talked about tangent a few minutes ago. Tangent does have restrictions at the domain at pi over 2 and every pi units to the left and right of pi over 2. So pi over 3 is in the domain. So you can go ahead and plug it in. Pi over 3 is a 60-degree angle. And so hopefully you remember how to evaluate the tangent of 60 degrees. So if this is 60 in the lower left-hand corner of the triangle, then I have 30 in the other acute angle. And my triangle has these 3 sides. Remember, tangent is opposite over adjacent. So the tangent of pi over 3 is root 3 over 1. And when you multiply that by 2, you get a limit value of 2 root 3. Okay, but what happens if A is not in the domain? So if it's not in the domain, that means you can't just apply direct substitution the way we did in the previous examples, but sometimes it's possible to simplify the function first and then apply direct substitution. So here are some examples. I want to evaluate the limit as x approaches 2 of x squared minus 4 over x minus 2. So clearly, if I plug in 2 in here, I'll have a 0 in the denominator, and we know that's not something you can evaluate. That does not have a value of 0. That's actually undefined. But that doesn't mean that the limit doesn't exist. So let's actually simplify this. We simplify this by factoring the numerator. So the numerator factors into x plus 2 and x minus 2. Now the x minus 2's in the numerator and denominator cancel, so I'm left with the limit as x approaches 2 of x plus 2. Then you can plug in 2, and so you get that the limit value is 4. So notice that I wrote the limit down throughout the time that I was simplifying, and the only time I stop writing the limit is when I apply direct substitution right here in this line. So that's the way your notation should be done with regards to limits. All right, now let's look at the example on the right, part B. So this one has a little bit more work to do. If you were to plug in -1 into the denominator here, you would again get 0, so it's not in the domain, but I can factor both the numerator and the denominator to see if it's something that will allow me to plug in the -1. So in the numerator, I have the difference of perfect squares, and in the denominator, I factored that trinomial into 2t plus 1 and t plus 1. That will give me the combination that I need above. Now the t plus 1's will cancel. The t plus 1's will cancel, leaving me with this result. The limit as t approaches -1 of t minus 1 over 2t plus 1. Now, if I apply direct substitution, I will no longer have a 0 in the denominator, so you get -1 minus 1 divided by 2 times -1 plus 1. That's -2 divided by -1, which gives me a limit value of 2. Again, notice that my limit is written here while I'm simplifying, but once you use direct substitution, you no longer write your limit. Okay. Here's another one. So here we want to evaluate the limit as h approaches 0 of this rational function. And again, if I just plugged in 0, I'd have trouble right away. That's undefined. So here I'm not going to factor, but I am going to expand the numerator. So expanding means that I'm going to FOIL the first term. So that gives me the first binomial. So that gives me 9 plus 6h plus h squared minus 9. Now the 9's will cancel, and that leaves me with 2 terms in the numerator, both with a common factor of h. So when I factor the numerator, I have h times 6 plus h over h. Then the h's cancel, and because that h cancels in the denominator, I can now apply direct substitution in for h. So I have 6 plus 0, which gives me a limit value of 6. Okay, so here we have a piecewise function. Let's sketch g of x equal to x squared when x is less than or equal to 0, and the square root of x plus 1 when x is greater than 0, and then evaluate the following limits and function. All right, so x squared is a parabola, but I don't want to show the whole parabola. I just want to show the part that's less than or equal to 0. So that's the piece right here. This is the piece x squared. We want a solid point here because it's less than or equal to 0 for x squared. And when x is 0, y is 0. Okay, then to plot the radical, I have the square root of x plus 1 for values of x greater than 0. So when x is 0, my square root of x plus 1 is 1. But here I have an open circle because it's just greater than 0, not greater than or equal. Then I got another point here. 3, when x is 3, your y value is 2, so this is a 0.32. And you should have a general idea of what this graph looks like because we've graphed square root functions before. So it looks like what you see on the right. So this is x plus 1. All right, so now we have to evaluate these limits. The limit as x approaches 0 from the left, well, that's when you're looking at the function on the left side of 0, and so that's um, your quadratic. And so by direct substitution, you can plug that in. And so that means that your limit value on the left side of 0 has a value of 0. When I'm on the right side of 0, well, that's when I'm looking at this part of the piecewise function, because right side of 0 means values greater than 0. And by direct substitution, I get a value of 1. That's what you see right here. That's that open circle. So as I get closer and closer to 0 on the right, your function value approaches 1. So what that means is that the limit as x approaches 0 does not exist because my left and right hand limits are different. But g of 0 does exist. To evaluate g of 0, you're looking at this part of the function because that's where x is less than or equal to 0. So when it's equal to 0, it has a value of x squared or 0 squared, which is 0. Okay. Here we want to sketch the graph of f of x and evaluate the following. So the function is another piecewise function, which is defined right here. F of x is equal to x cubed when x is less than 1, and it's equal to 2x minus 1 when x is greater than 0. All right, so x cubed, when x is less than 1, your x cubed function looks like this. Remember, the entire x cubed function looks like this over all real numbers, but we only want the part to the left of 1, so that's the bottom part of this graph. And then 2x minus 1, well, that's a line. At 1 has a value of 1, but it's open here because I have both a less than 1 and a greater than 1. It's never equal to 1 in this piecewise function at all. And then with a linear function, you just need one other point. So I plugged in 2. When x is 2, if you plug it into this function, you get a y value of 3. So this point here is the point 2, 3. Remember, you only need 2 points to graph a line. So I use the open circle and the point 2, 3 and connect it to make my line. Okay, so the limit as x approaches negative infinity. Well, as x approaches negative infinity, if I look at what my function is doing, it's going this way. So this is going towards negative infinity as well. The limit as x approaches 1 from the left. Well, when I'm on the left side of 1 and I look at my function value, it's getting closer and closer to my open circle, which is also 1. When I get closer and closer to 1 on the right, again, on the right, I'm getting closer and closer to that same value, which is also 1. Therefore, the limit at 1 exists. It's equal to 1 because the left hand and right hand limit above are the same. And as x approaches infinity, right, this way is infinity, this way is negative infinity, my function is going in this direction, and so this is going towards infinity. Okay, so that's it for this lesson. You should try the homework. So good luck.